Hello everyone. Let us discuss about the derivation of stiffness matrix of beam element. So I have considered here a beam element uh, consisting of node 1 and node 2 having displacements, vertical displacements V1, V2 corresponding to node 1 and 2 and rotations corresponding to node 1 and 2 are theta 1 and theta 2. So in the previous lecture, I have discussed about the shape functions related to the beam, having the shape function h1, h2, h3, h4. So these equations were derived, and we also know that field variable in general it is given by v is equals to h into q, where h is consisting of h1, h2, h3, h4. h2 and h4 are associated with the slopes, so therefore they are multiplied with Le by 2 into the displacement vector of the beam element consisting of q1, q2, q3, q4 or v1 theta 1, v2 theta 2 terms. So to derive the stiffness matrix of beam element, let us consider the strain energy for beam. It is given by EI by 2 integration over the volume V, dou square V by dou x square whole square into dx. And V, as we know, it is equals to H into Q. And to have the stiffness matrix, let us differentiate as we need dou square V by dou x square. Let us differentiate this V with respect to x. So dou V by dou x or dV by dx can be written as dV by d zeta into d zeta by dx. We know that for a 1D element, the global and natural coordinates are related by zeta is equals to 2 times of x minus of x1 divided by x2 minus of x1 minus of 1. And therefore, uh, dou v by dou x can be written as dou v by dou zeta, and differentiation of zeta with respect to x is given by 2 times of length of element. So dou zeta by dou x or d zeta by dx is 2 times of Le. So dou v by dou zeta into 2 by Le is nothing but dou v by dou x. So dou square v by dou x square can be written as dou square v by dou zeta square into square of this. This is 4 by Le square. Its whole square, that is dou square v by dou x square whole square, can be written as 16 by Le to the power of 4 into dou square v by dou x square whole square. So therefore, this can also be written as dou square v by dou x square whole square can be written as 16 by Le to the power of 4. V double dash of a q, it's a square. Or V double dash of q can be written as dou square v by dou x square or d square v by dx square. Or V of q, we know that it is h into q. And V double dash of q will be h double dash into q. So V double dash q whole square. Whole square can be written as transpose into the term. It is h double dash transpose into h double dash. It represents the square term, and q transpose into q will be the whole square of V double dash q term. So V double dash q whole square can also be written as q into h double dash transpose h double dash into q transpose. We have the value of h1, h2, h3, h4. So what we need is double differentiation of h1, h2, h3, h4. So I have written here h1 differentiated twice with respect to zeta. So we'll get 3 by 2 zeta. It is h2 differentiation of h2 2 times with respect to zeta. We'll get 3 zeta minus of 1. Similarly, consider h3 differentiate with respect to zeta twice. We'll get minus 3 zeta by 2. Consider h4 differentiate this with respect to zeta twice. We'll get h4 double dash as 3 zeta plus 1 divided by 2. So we know that h is nothing but h1 Le by 2, h2 h3 he Le by 2, h4. So we have the terms of double differentiation. So h double dash can be written as h1 double dash, which is nothing but 3 zeta by 2, h2 double dash, which is 3 zeta minus of 1 divided by 2. Here we have to multiply Le by 2 again. So minus 3 zeta by 2 and 3 zeta plus 1 by 4 into Le. This corresponds to h4 double dash. So h4 double dash terms given by this matrix. So therefore, V double dash square, as it is written as Q transpose H double dash into H double dash transpose into Q, which is multiplied by 16 by Le to the power of 4 in the equation 2.8.10 EA. So therefore, strain energy will be equals to I have just substituted the value, that is 16 by LE to the power of 4, in the integration over the length LE, H double dash transpose dx into Q. To substitute the values as dx is equals to d zeta Le by 2, strain energy can be written as half Q transpose K into Q, to where K is the stiffness matrix and the stiffness matrix of beam element is given by this. That is, separate the terms of K other than Q and Q transpose and half. So Q transpose half, other than this, the terms consisting of EI by LE to the power of 4 into 60 in the integration of -1 to +1, H double dash transpose into LE by 2 into d zeta, or it is K is equals to A Ti by LEQ in the integration -1 to +1 H double dash transpose into d zeta. To H double dash we have this equation or this matrix. Multiply this with H double dash transpose. So this is the matrix. So when you multiply these two matrices and if you substitute the limits from -1 to +1 after integration, you will get the stiffness matrix of beam element as ATI by LEQ in the matrix of 12, 6 LE, minus 12, 6 LE, 6 LE, 4 LE square, minus 6 LE, 2 LE square, minus 12, minus 6 LE, 12, minus 6 LE, 6 LE, 2 LE square, minus 6 LE, 4 LE square, where K is the stiffness matrix, E is the Young's modulus of the material of the beam, I is moment of inertia, and LE is the length of the element. So I will just have the overview of the stiffness matrix of beam element. First of all, you have to consider the safe functions, and we know the field variable as V is equals to H into Q. H can be written as H1 Le by 2 H2 H3 Le by 2 H4, and Q is nothing but displacement vector, which is Q1 Q2 Q3 Q4. And we have to consider the strain energy for beam element, which is given by EI by 2 integration dou square V by dou square dou x square whole square into dx. So for this, we have to consider the field variable, and dou v by dou x can be written as dou v by dou zeta into dou zeta by dou x from the chain rule. So zeta here is the relation between natural and global coordinate, which can be written as zeta is equals to 2 times of x minus of x1 divided by x2 minus of x1 minus of 1. So differentiating this zeta with respect to x, we'll get 2 by x2 minus of x1, or x2 minus of x1 is nothing but length of element, that is 2 by LE. So dou v by dou x can be written as dou v by dou zeta into 2 times 2 divided by LE. So for this, what we need is dou square v by dou x square. So we can have another differentiation here, and square of this will be this term. So v double dash q whole square can be written as h double dash transpose h double dash q into q transpose. So here, what we need is double differentiation of h terms. So h1 you have to consider. For that, you have to differentiate twice with respect to zeta. Similarly, h2, h3, h4s are considered and differentiated with respect to zeta twice. So ultimately, H double dash is having this matrix. So transpose of this will be a column matrix. So when you substitute all these terms in V double dash whole square equation, you will get this. And in general, strain energy is written as half Q transpose Ke into Q, and Ke term is separated here. And ultimately, when you substitute the terms of H double dash and H double dash transpose, and when you multiply and integrate with respect to with the limits of -1 to +1, then we'll get the stiffness matrix of B. Now, next is about the derivation of load vector due to uniformly distributed load. I have considered a beam, and for this, UDL is acting over its entire length of intensity P naught. So, in general, work potential is for a UDL load, that is surface force, is integration over the length of element P naught into VdX. So, V is nothing but HQ. H is consisting of H1, Le by 2, H2, H3, Le by 2, H4, and Q is the displacement vector associated with V1 theta 1, V2 theta 2. So I have just substituted V term, that is H into Q here, and dx is nothing but Le by 2 d zeta. With the relation, you can find this. So work potential is therefore equals to integration from -1 to +1 P naught LE by 2, P naught LE by 2, H into Q transpose into zeta. So here we have just substituted the dx value with LE by 2 d zeta. So therefore, work potential can be written as Q transpose integration from -1 to +1 P naught LE by 2 into H into d zeta. So work potential due to traction force in its standard form can be written as it is Q transpose into load vector due to T. So that is traction force or surface force. So traction force is therefore equals to integration. When you compare this with the previous equation, so it is integration from -1 to +1 P naught LE by 2 H into d zeta. So H terms we know and into d zeta. So ultimately when you integrate this with and substitute the upper and lower limits, we will get T is equals to P naught LE by 2 P naught LE square by 12, and there is a slight correction, it is 12 here, and P naught LE by 2 minus P naught LE square by 12. So the load vector due to UDL is P naught LE by 2 P naught LE square by 12, P naught LE by 2 minus P naught LE square by 12. This is corresponding to V1 direction, this corresponds to theta 1 direction, this corresponds to V2 direction, and this corresponds to theta 2 direction. So this is the load vector. So here what we got is the safe functions and stiffness matrix, then load vector due to UDL. So thank you for listening this video. Thank you.